All right, so what happens on a logistic model is the basic idea is, I think, like last class period, we were working kind of with exponential. We were doing this stuff with cells, and it's not very realistic. So like if you had, let's use rabbits as an example. Rabbits reproduce real fast, okay? I mean, that's how they survive, because if they don't, they're going to all get eaten and die. So like what happens, if you model a population, it's not realistic for populations to exponentiate forever. Otherwise, we'd have nothing but rabbits and filling up the whole universe, right? What happens is there's a carrying capacity. There's not enough food. There's predation, all kinds of things. So what tends to happen is it levels off. So that's what a logistic regression tends to look like. Exponentiates for a while, then it starts kind of leveling off like that. So a lot of times logistic models are a better long-range indicator of how populations go. Okay, so a logistic model follows this function, P of t, and you have c over 1 plus a e to the negative bt. And if b is greater than 0, that makes logistic growth, which is what I'm going to talk about mostly. Then you can also have logistic decay if that b is negative, okay? So what I'm going to do is just do one example that just kind of gives you a basic idea of what this is. The idea, first of all, with this, there's a couple of things that are probably worth you writing down. Like this C is called the carrying capacity. That's worth writing down. So that's kind of like a horizontal asymptote. That's actually what it is. It's a horizontal asymptote. And that just kind of tells you how the graph is behaving at infinity. Okay, so that's a carrying capacity. Okay, so the other thing in here is B is just like a rate of growth. So B is like the growth rate or the decay rate. Okay, and then A is usually just some sort of a mathematical constant. Okay, so the idea with this is, like in this particular logistic model here, if this is a logistic model, the carrying capacity would be what? 500. Okay, so we just say 500 is going to be the carrying capacity on that. Okay, and what again that means is as t goes to infinity, as t gets bigger and bigger, then p of t, the function, gets closer to 500. It'll make perfectly good sense once we do a graph. Okay, all right, the growth rate in this particular problem, what's the growth rate? Yeah, negative 0.162. Okay, that's your growth rate. Okay, so usually you write that as a percentage like you've been doing. So if you moved that over, that would be about 16.2%. And then since it's negative, that would actually be like a decay because that is negative. Okay, so that's a growth rate. That's just kind of the standard part of that. Now what I'm going to have you do is get your calculator out. I'd like you to graph this with me. I'm not going to graph this thing any other way. This is not some standard function with transformations like we've learned. So I'll put it up here, and I'm back in sequence mode from Calc 2 again. So let me fix that real quick. Okay, so let's see. Just put it exactly like it is. Okay, now what you want to do is be sure that you put the denominator in a big set of parentheses, so it does this right. So I'm going to start with a big set of parentheses. I put in 1 plus 83.33. Then I got e, so you can go to the second of the logarithm, natural logarithm, to get that put in. And then if you have a calculator that does a superscript like mine, if you have an 83, you'd have the little caret, and you'd have to put this in parentheses. I think most of you've got a calculator that does that superscript. So all you got to do is just put in negative 0.162, and then you got to put your variable in, and we'll have to put x in this case then. Okay, and then close the parentheses, and that should be what you want to get in your calculator then. Okay, yeah.
I just had a question. So for the last one, you said it was decay, but since the variable is actually negative in the equation, wouldn't it be 0 because it came out as negative? If it was decay, then the...
Oh, I got you. You're exactly right. And I wasn't paying attention to that. What happens is within the formula, it's already negative, right? Okay. So what happens is that's already negative. So B is actually just this little piece right there. Okay. Do you see what she's saying? She's right. Okay. So that would end up being a growth rate. And that's what we would expect anyway. I should have caught that. Because if it's decay rate, you start with a whole bunch of eagles and they all die. That's sad, okay? So it doesn't go like that, okay? They're going to grow and level up. Thank you. So yeah, the growth rate on here, this is a growth rate, not a decay rate, okay? All right, now let's go ahead and let's set up a window. So first of all, think a little bit about the Y value. The carrying capacity is 500. So I said that's a horizontal asymptote. So on the Y, it would make a lot of sense. I'm going to go ahead and just have you put in 0 to 600 because I know about that, the carrying capacity that's built into that. And then I'm just going to take kind of an educated guess on the X's. I'll adjust it if I have to. I'm going to go, as it's time, maybe I'll go 0 to 100, maybe scale by 10. And what we're looking for is kind of, it exponentiates for a while, then it starts leveling off, okay? So I'm going to slide this over here so you can see that. I'll type in the graph and let's see if that looks good. That's a good guess, okay? So that's kind of what happens. And this is the way populations work more often than not, like in the bacteria. Okay, yeah, once it runs out of room and stuff like that, it starts leveling off. So you have that. You have that type of graph like that. So let's just do a real rough sketch of this. And then the rest of the parts of the problem, mainly what we're going to do is use our calculator to solve this. So let's do just kind of a quick, simple graph on here. And there's some things I want you to label. So we have the time as that. This problem doesn't say anything about time, whether it's days or years or whatever. So I'm going to just assume that's years. I think that's what that is. And then this would be the population. This is P of T. So P of T is just going to represent the number of eagles in some population, maybe at a park or something like that. Okay, and what we find on this is we went all the way up to, I think, 100 here. And we just need to get a couple of key pieces of information. Then I'm going to go 1, 2, 3, 4, 500. And that's kind of the key on that. And then let's just get maybe like 3 or 4 good points. Okay, so let's trace at some of them. If you trace at 0, that would be the initial on that. So that's around 5.9, somewhere in there. This is 100 like this. So just put a dot way down low like that. Then let's go out maybe to, let's go to about 30. I'm going to trace maybe at 30. Okay, and that'll give me about 30 and a little over 300. So I'm going to put that in. Okay, and just label that. So that looks like over 30 and up a smidgen over 300. And then I'll just have you label that point. That's about 304. I'm just going to round that off like that. And then let's do one other one. Let's do like, let's do 50. I'll trace at 50. And notice now by the time you're getting to 50, it's starting to get close to 500. Then it's going to level off. So with this one, let's just plot that point. You have 50, 487. Label that point, and then the rest of it we're just going to sketch. So that's about 488 eagles like this. So what's happening is it kind of starts its exponentiation, then it levels off like that from then on out. Okay, so that's the idea. Does that make sense to everybody? Okay, that's what a logistic growth model tends to look like. Okay, and it's more realistic because of the carrying capacity. Okay, all right. Now what we're going to do on the next thing here is, if you wanted to find the population in 3 years, well, you have 2 ways you could do this. And we're mainly just going to do this on our calculator. All you got to do now that you got your calculator, instead of plugging in the 3 into the function, which you could do, you should just have to trace in, just type trace 3, and it'll give you the answer of the problem. So after 3 years, you can see that that's giving us about 10 eagles, okay, 9 or 10. Okay, it's not half of an eagle, so just take your pick, okay? All right, and that gives you the basic idea, all right? Okay, and then the next page we're going to do a couple of things, mostly with our calculator, and I want all of this kind of problem to be done with technology because the math gets a little tricky with logarithms and stuff like this, so it's better suited for technology. Okay, let me see if you can figure out how to do this with the calculator. Okay, what we're trying to find is when you'd have 300 eagles. With the calculator, what do you think you would do?
You calculate the intercept.
I would just graph 300, right, and find the intercept, exactly. So what we're going to do with this is just go to y equals, and then do 300. See, this way you don't have to solve an equation. You could do this with your calculator. So yeah, you just do this intersection point right here, and that will tell you how long it takes for that population to reach 300. So we just go second, calculate, intersect. You'll have two cursors come up, and then just keep pressing enter, and then it'll give you the answer. So it looks like on this one, you're going to end up getting x is about 29 or 30. I'll just say it's close to, let's just round that maybe. This is a time, so that's 29.8 years like that. Okay, so that's the idea. Okay, that problem would be fairly complicated to solve with logarithms. I mean, it could be done, but this is better suited for technology to me. Okay, and then one last problem. I want to look at how long does it take for the population to reach 1/2 of the carrying capacity. That's almost the same thing that I just did, with what exception? What is 1/2 of the carrying capacity? 250, right. So what we'll do on this is, and since we're using technology, we just graph out the 250 and we do exactly the same thing, okay? So that'll come out, and this will give you the halfway point of the carrying capacity, and then what you should have to do is just do the intersection like we did on the last problem, and then you're all set. Okay, so that looks like that happens about, where's my cursor? I don't see my cursor anywhere. Is that what you guys are getting? 27.3? Looks like my cursor's not there for some reason, so that looks good. Okay, so 27.3 years approximately is what you have there then. Okay, that problem I want is just an introduction to a logistic model. That's all I wanted to do with that, okay?